Hello friends, in this video I'd like to solve the following problem from the Polish Mathematical Olympiad, first round 2011, problem number 2. We wish to find all non-negative integers x and y such that 2 to the power of x plus 5 to the power of y is a perfect square. So it's a nice number theoretic problem, here are my hints. First, consider y to be 0 and write that then 2 to the power of x equals k minus 1 times k plus 1 and try to solve this equation. But for y greater than or equal 1, consider first reduction modulo 5 to find the parity of x, and then consider reduction modulo 3 to find the parity of y. Consider x equals 0 and x equals 2 separately. And for x greater than or equal 3, consider reduction modulo 8. And that should be enough. So give this problem a try. Alright, so let's start. So I wish to consider case number 1 when y equals 0. When y equals 0. Notice that then our equation can be rewritten in the following way. 2 to the power of x equals k squared minus 1, because 5 to the power of y is 1. I put 1 on the right hand side. So we have 2 to the power of x equals k minus 1, k plus 1. And notice that, and we can write that k is a positive integer. Alright? And now notice that these two numbers differ by 2. So both of them cannot be at the same time divisible by 4. So k minus 1 and k plus 1 cannot be both divisible by 4. And moreover, k minus 1 and k plus 1 are of the same parity. Or maybe, you know what, no, don't write it. Maybe from there we know that we have two options. Either 2 to the power of x, either k minus 1 equals 1 and k plus 1 equals 2 to the power of x, or second option, k minus 1 equals 2 and k plus 1 equals 2 to the power of x minus 1. We cannot go further because for x greater, for example, if we have 4 right here, then 2 to the power x minus 2, well, either it's going to be less than 4, and we have contradiction because k is positive, or it is greater than or equal 4, and we have contradiction because both of these numbers are divisible by 4. For the first equation, after subtracting, we get that 2 equals 2 to the power of x minus 1. So 3 equals 2 to the power of x, clearly contradiction. But in the second case, after subtracting, we have 2 equals 2 to the power x minus 1 minus 2. 4 equals 2 to the power x minus 1. And right here we have one solution, x equals 3. Alright. So let's consider now case number 2 will be when y is greater than or equal 1. Then we will do reduction modulo 5. Reduction modulo 5. Notice that 2 to the power of x should be congruent to k squared modulo 5. Because 5 to the power of y is gone. It's divisible by 5. And now, let's consider all the possible quadratic residues modulo 5. Notice that 0 squared is congruent to 0, plus minus 1 is congruent to 1, plus minus 2 squared is congruent to 4. And what about 2 to the power of x? 2 to the power of 0 is congruent to 1, 2 2 to the power of 1 is congruent to 2. 2 to the power of 2 is congruent to 4. 2 to the power of 3 is congruent to 3. And we have repetition going on from there. From there, we see that the only possibility for this congruence to be true is that x must be even. X must be even. And now, let's consider further reduction modulo 3. And we'll have, let's take a look, we'll have 2 to the power of x, but I can write it as 4 to the power of x over 2 plus 5 to the power of y is congruent to k squared modulo 3, which really 4 is congruent to 1, so we have minus 1 to the power of y is plus 1 is congruent to k squared modulo 3. Now, when is it possible? Well, once again, let's consider all the possible quadratic residues modulo 3. 0 squared is 0, plus minus 1 squared is congruent to 1. And notice that 1 plus minus 1 to the power of 0 is congruent to, and 1 plus minus 1 to the first power is congruent to 0. From there, and its repetition is going on from there. From this, we see that y must be odd. Y must be odd. Alright. And now I wish to consider two more separate cases. When x equals 0, then we have the following equation. 5 to the power of y equals k squared minus 1, which is k minus 1, k plus 1. And once again, notice that these two numbers differ by 1, so only one of them can be divisible by 5. So maybe let's write it k minus 1. Write it in a different color. And let's write it in yellow. K minus 1 and k plus 1 cannot be both divisible by 5. So we have only one option, namely k minus 1 must be 1 and k plus 1 must be 5 to the power of y. But then after subtraction we have 2 equals 5 to the power of y minus 1, 3 equals 5 to the power of y. Clearly contradiction. No solutions. Alright, what happens when x is equal to? When x equals 2, notice that there is no need to consider x equals 1 because we know that x is even. When x is equal to, then 5 to the power of y equals k squared minus 4, which is k minus 2, k plus 2. And notice once again, these two numbers, k minus 2 and k plus 2, differ by 4 this time. So still, they cannot be both divisible by 5. Which means, once again, that we have only one option. K minus 2 must be 1, and k plus 2 must be 5 to the power of y. After subtraction, we get 4 equals 5 to the power of y minus 1, and from there, we see that y equals 1. We have another solution. And the last case, when x is greater than or equal 4, then what we do reduction modulo 8 this time. And notice that now we have 5 to the power of y is congruent to k squared modulo 8. Because 2 to the power of x is greater than or equal 4, well, it's of course divisible by 8. And now, once again, let's consider all the possible quadratic residues modulo 8. 0 squared is congruent to 0, 1 plus minus 1 squared is congruent to 1, plus minus 2 squared is congruent to 4, plus minus 3 squared is 9 is congruent to 1, and 4 squared is congruent to 0. And what about 5 to the power of y? Notice that 5 to the power of 0 is 1, 5 to the first power is 5, congruent to 5, and then we have a repetition, because 5 squared is 25, but 25 is congruent to 1 once again, and we have a repetition. And now we see a problem, because remember that y is odd, so the number right here must be congruent to 5. But 5 is not on the list on the left hand side. So in this case, we have no solutions, because we must have 5 is congruent to 0, 1, 4 modulo 8. None of this is true. No solutions. So all in all, we have found exactly 2 pairs of solutions. X equals 2, y equals 1. And first, we have found 3, 0. And these are our solutions. And really, this closes our problem. Our Diophantine equation has exactly 2 pairs of solutions. And that should be it. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.